Good morning, parents and any teachers who may be watching. Welcome to Creating Math Ahas for Parents. In this video, we're going to take a look at double-digit multiplication using the area model. Now, double-digit multiplication typically is something introduced in grade 4. The area model is a model that we can use to solve multiplication problems, but it is a very important model because it also leads us to the distributive property. It's a great visual image for that. So one of the key models we use to represent that area model, we can use base 10 materials. Now, you may have seen these in other videos. We have the hundreds, the tens, and the ones. For me, when I start working with double-digit multiplication with your children, I tend to use paper versions. Now, if you want these for your child to use at home or to work with later, these are just made from centimeter grid paper. And I use different colors to help highlight the tens, the hundreds, and ones, but that's not the important thing here. The important thing here is that I can flip them over and have the blank sides with paper. These models, when I flip them over, turn them, I hope you can see the lines always remain. So you'll see how we use these models to help your child with the double digit. I'm going to do some examples. I'm going to start with a double digit end result type problem, and then we'll move forward from there. So let's look at the problem 23 times 35. Now, for double digit multiplication, it's important that your child understand expanded form for a number and use it because it helps us get to much more efficient drawings, efficient pictures. So in this case, 23 in expanded form would be 20 and 3. And you can also think of it as a place value form for the number, right? We have 20 and 3, not 2 and 3. For 35, our expanded form would be 30 and 5. Okay, so that's one thing to look at. The other thing is to understand that this model is powerful and efficient, and it uses relationships of the facts. For example, if I know 2 times 3 is 6, then I know 23s is going to be 60. Or I know that 2/30s is going to be 60. See, I can use the fact I know to find out the answers when I multiply by multiples of 10 or 100, those powers of 10. Then I also know 20 times 30. Now, looking at multiplication facts and the development of those, that's in a different video, and I'll leave you the link to the multiplication playlist below. But that will be used, this idea of facts will be used here. The other idea is that area is additive. And what that means is, suppose you're trying to change the flooring in your house and you're going to put the same flooring throughout. You can find the square footage of each room and then add it together and get the total square footage, right? You find the area and then you add them together. Same thing, if you have a rectangular room, and you want to create some design with your flooring, you can find the area of the design piece, the area of the rest, and that total, you put them together, you should get the total area of your room. So that means I could cut up a room. I could cut up an area into smaller pieces and find the area of those pieces and add them together. So in this case, we're going to suppose that we have a rectangular room that's 23 by 35. And 23 times 35 is a little more challenging to do in my head, but see, I can cut this room using this expanded form. I can think of 20 and 23 as 20 and 3. See, I'm going to cut it across. And I can think of 35 as 30 and 5. Make a cut. Okay. Now I apologize that my drawings might not be to scale, but they're a sketch, and I hope that at least you get the idea from this. Now, if you look at these, this rectangle is 20 by 30. This rectangle is 20 by 5. This one's 3 by 30, and this one's 3 by 5. See, we use this idea then to find the area of each of the pieces. I know that 20 times 30, I can do that one if I know 2 times 3. So this area is 600. A 20 by 5 is 100. If I know 2 times 5 is 10, I can use that. 3 by 30 is 90. And 3 by 5 is 15. And I can add all these together, and I get the total area. So if you think about this, well, 600 and 100 is 700. The 90 and the 10, that's going to be another 100, 800. And then I've got 5 more, 805. So 23 by 35, that has a total area of 805. And I found it by using this area, this idea that I can cut that area into smaller pieces. Now, the nice thing with that, see, I mentioned this gets us to the distributive property. See, notice what I have here. I've thought of that 23 as 20 by 3. I've thought of 35, 20 and 3, should be a plus, as 30 and 5. Now, some of you remember a mnemonic, FOIL. We shy away from that now because it only works for specific instances. But think about, what do we have? 20 by 30, right? 20 by 5, 3 by 30, 3 by 5. It is the distributive property. I have a 20 by 30 put together with a 20 by 5, put together with a 3 by 30, put together with a 3 by 5. So there's an area model, double-digit multiplication. Now, before I go any further, just some formalities. If you're finding this video useful, if you would please give it a thumbs up, that would be great. Share it with colleagues, share it with other parents if you think it would be helpful to them. That would be fantastic and really help out a lot. But I want to show you, just take a moment, of how we help your children get to here and how to help your child get to this point, okay? So one of the ways we help your children progress to that image for the double-digit area model is we start in grade 3 typically with just introducing what rectangular area looks like. You see, I've used those base 10 ones to do a 2 by 3 rectangle. And what we do at first, we have your child draw the model for a 2 by 3 rectangle. Right? And you see you have all the squares. So they can see it's a square unit measure for the area. This is a 2 by 3, the dimensions, or another way we could write 2 by 3 is this. Total area, 6 square units. All right. So we get them very comfortable with 1 digit by 1 digit multiplication in grade 3. Eventually, we transition them from drawing in all those lines to just having the 2 by 3, but picturing those square units in it. So they still connect this to that, picturing the lines. So we do enough activities with them to get them used to that. Now we can transition. Let's say, I'm just going to shift these down a little bit. Now I want to look at a 12 by 3. Okay, now do you see the color? Hopefully that glare's not too bad. See the color difference there? And again, I have your child typically, and you have them at home if you can, build it and then draw what they see. Now, some children, they'll try to trace this and draw it the exact same size. And we need them to understand that the sketch doesn't have to be the exact same size. It can be a shorter image than that. But if you look at what we have with some of your children, they may see all the individual squares and they'll have this 3, right? But they'll figure out a way to cut it into 12 equal pieces. How did I do, right? 2, 4, 6, 8, 10, and 12. Now, if you look at this drawing versus this image, I don't account for the color here. Now, I could draw this in here to show where it splits with the color. But this particular image tends to have your child wanting to count all the squares. So once they get comfortable with this, what we're wanting to do is help them transition from that drawing in all the squares to a drawing more like this. Now you see what that lets me do is think of this 12 as 2 and 10, right? I've got 2 3s put together with 10 3s. Or if I turn it, 3 2s put together with 3 10s. In any case, this is the drawing. This model, for some of your children, it's hard for them to see this whole when they see all the squares outlined. But that's where this helps us because we can turn it over. Now do you see where that paper is helpful because it lets us go from seeing all the squares to here. So this is going to be 1 digit by 2 digit. And I can do this for all types of numbers, but do you see how we're moving from this more efficient to just the outline, from this going more efficient to using expanded form, the 2s and the 10s. And then we can progress it one step further. We could take this, and I'm going to keep it 12 high, but I'm going to put these down here maybe, huh? Because what I'm going to do here, and let me turn these back over, is this time I want my rectangle to be 12 by 13. Now, you know, your children may want to grab an awful lot of these and make a 12 by 13 rectangle. And there's absolutely nothing wrong with that. Mathematically, that's fine, but it's not the most efficient representation. See, we have the hundreds. So this is 13 wide and 12 deep, okay, tall. This is a 12 by 13. Now, I hope you see I don't have to have the 10s here and the 100 here. I could turn this around in lots of different orientations. Okay, so, you know, the rectangle could be here. This is a 13 by 12, technically, for many. Here, I could have had it like this. I could have it like this. The important piece is it's got to be a solid rectangle. So for some of your children, they may have 12 and 13, but there's a hole. And they have to fill it in with those little squares. So you'll see them filling it in. Now again, if I have, or we want them to fill it in, if I have that 12 by 13, okay, Some of your children will again try to draw all those squares, or they'll even do, let's say we have the 3 10s, the 2 10s, and that 100. Now that's not such a bad drawing for 12 by 13. And we see we're thinking of this, and I could draw it this way. Might be easier to do it in the order for some, right? If I have this drawing, is it easier for some of you to see the 10 and the 3, the 10 and the 2? Doesn't matter. I can do that mirror image. So I'm thinking of 13 as 10 and 3. I'm thinking of 12 as 10 and 2. And I can find area of each of the pieces. The 10 by 10 is 100. Those 10 threes, 3 10s is 30. 2 10s, 20. 2 3 6. But you see, if I get up to a problem like 18 by 28, I'm going to end up with 64 little squares drawing in. Not a very efficient. So at first we let them do this, and I would typically do this when my factors are 15 or fewer. Okay, give them the idea. But when we're getting up here where the ones place is above 5, gets less and less efficient. So this drawing's better than drawing all the squares, but see, I can transition them from there to here. Think of this as 10 and 2. Think of this as 10 and 3. Just do the outlines. And just like before, I could have flipped these over to help with this drawing, flip the 10s over to help. So that transitions them here, and then we get to this one. But ultimately, when we get to problems like the 18 by 28 and what we eventually want them to do, just give you another example. We're going to think of 18 using expanded form. So we can think of 18 as 10 and 8. We can think of 28 as 20 and 8. We draw the rectangle. And I'm drawing a wide rectangle. Usually for this, the vertical dimension is the first one. Horizontal is the second. It's vertical by horizontal. That's kind of a norm that you may see used. I could turn this, and this would be my 28 by 18. And then it's still the same idea, right? A tall rectangle or a wide rectangle. But I'm going to think of 18 here as 10 and 8, and I'm just going to cut it across. I'm going to think of 28 as 20 and 8. And then I'm just going to cut it down. Now, some of your children may want to think of 28 as 10, 10, and 8. And that's a great intermediate step. That's fine. Mathematically, it's correct. It's just not going to be the most efficient. Most efficient will be this expanded form. So we just move them towards that. But if they start out and they're thinking of 10, 10, and 8 because of the base 10 materials, fantastic. That's fine. But now you see, I know what 10 times 20 is if I know what 1 times 2 is, right? I've got 200. I've got 80. 10 eights or 8 10s. I've got 160. 8 20s or 20, right? This is an 8 by 20. And an 8 by 8 is 64. So I add these up. This was my 28 dimension, right? This is my 18 dimension. I add these together and I get my total, my product, okay? So you can do this in your head, you can do it on paper. Essentially, we've got here 240, 440, and that 60 gives us 500. So we're at 504, I believe, okay? If you want, your children may want to write the partial products, 200, 160, 80, 64. The partial products are just the product of each of those pieces. I can add those together. If you want to do it more of a traditional way, we have 4. We have 60 and 80 is 140, and 60 more is 200. So we've got 200s, and 200 is 400, and 100 more is 500. Notice how I'm using place value language each time. So I could add the partial products together. I can use different algorithms. I can use a traditional in grade 4. Earlier, we might use a place value one where you heard my language, where I'm thinking of it that way. And I could have done partial sums. You may see another way of writing this, which is just as accurate, is you may see a child, I'm going to call it partial sums, and I can go either direction. 100 and 200 is 300. 60 and 80 is 140, and 60 is 200. And then I have the 4. See, partial sums. I'm using place value. No matter how I do it, I'm still coming up with 504. And this is the area model for multiplication, 2-digit by 2-digit. 3-digit would be similar, except I'm just going to cut it into 3 sections, okay? So again, I hope this video helps. If so, please give it a thumbs up, share it with your friends, subscribe to the channel so you know when other videos are coming. Thanks so much for watching.